ফার্স্ট শুভ নববর্ষ টু অল মাই ভিউয়ার্স। আজি নূতন রতনে ভূষণ যতনে প্রকৃতি সুধীরে সাজিয়ে দাও। ভেরি হ্যাপি অ্যান্ড প্রসপারাস পয়লা বৈশাখ। মে দিস নিউ ইয়ার ব্রিং ইউ গুড হেলথ, হ্যাপিনেস, সাকসেস in your life. In my previous video, I had seen improper integral and test of different type of improper integral. Today I will see this topic elaborately. In my previous video, I had seen comparison test of improper integral. Today I will see at first the limit comparison test of improper integral. Then I will see different type of example of improper integral and various type of other test to find one improper integral be convergent or divergent. Let's see first example. Our first example, determine all values of p for which the improper integral converges. 1. Integration 1 to infinity 1 over x to the power p dx. 2. 0 to 1 integration 1 over x to the power p dx. For which value of p this true integral converges. At first consider p equal to 1. For p equal to 1, integration 1 to infinity 1 over x dx equal to limit b tends to infinity integration 1 to b 1 over x dx. This is equal to log x, and here integration from b to 1, and after evaluating this value would be log b minus log 1, and we all of us know log 1 tends to 0, and when b goes to infinity, then log b obviously goes to infinity. So this integral is diverges. Okay, and when integration 0 to 1 over x dx, this we can write limit c tends to 0 plus integration c to 1 over x dx, and this is obviously similar to before log x. Here integration 1 to c, after evaluating this value, this would be log 1 minus log c, and limit c goes to 0 plus, and when limit c goes to 0 plus, then log c obviously goes to minus infinity, but here minus sign, so this is goes to infinity, so this is also diverges in this interval. Therefore in this interval both integral are diverges. Previous video I have seen direct comparison test in improper integral. As per review, I have seen comparison test is let f and g be two continuous function on the interval closed a open infinity with the condition 0 less than equal to fx less than equal to gx, and this is true for all x greater than equal to a. Then statement 1, if integration a to x gx dx is convergence, then integration a to x fx dx is convergence. Second, if integration a to x fx dx diverges, integration a to x gx dx is diverges, and this is the picture, this is fx and this is gx. If top of the function b converges, then that imply middle fx always converges, or if middle function fx is diverges, then that imply top function fx always be converges. This is the statement of comparison test. In my previous video, I have defined this test elaborately. Today actually just a review. Today actually I will see what is the limit comparison test. As for example, consider this integration 0 to infinity cos x over 1 plus x squared dx. We all of us know cos is less than equal to 1 for all x belongs to R. Okay? Hence, cos x less than equal to 1 for all x belongs to R. So obviously, this is less than equal to 1 over 1 plus x squared. So, consider fx equal to this function and gx equal to 1 over 1 plus x squared. Then we have to show is gx is convergent comparison test. If gx is converges, then obviously fx is convergent. Integration 0 to infinity dx over 1 plus x squared equal to limit b tends to infinity integration 0 to b dx over 1 plus x squared. And this value is actually tan inverse x, and in the limit, if we apply the limit, then this value would be pi over 2. So, since the value of integral is finite, that means this integral is by comparison test, we can tell this integral is convergent. Okay? I hope my all viewers have understood this question easily. Okay? Oh well. Now let's come back our original discussion. Limit comparison test. What is limit comparison test? If possible function f and g are continuous on the interval closed a open infinity, and if limit x tends to infinity fx over gx equal to L, where L lies between open 0 and open infinity, then integration a to infinity fx dx and integration a to infinity gx dx both converge or both diverge. And here one thing noticeable, here I have evaluated limit as x tends to infinity. I have evaluated limit as x tends to infinity because at the point infinity, this function has a discontinuity. But if we consider 0, a, this type of interval, and if there exists discontinuity at the point 0, then this limiting value would be limit x tends to 0. That means in which point the function has a discontinuity, we have to find limit at this point. Okay? I hope my all viewers have understood limit comparison test easily. Okay? Now I will see one question of limit comparison test. Integration 1 to infinity x squared plus 1 over x to the power 5 plus 4x to the power 4 plus 10 dx. Consider this function. Here I will use the limit comparison test. For limit comparison test, consider gx equal to 1 over x cube. And consider this is the fx function. Then limit x tends to infinity fx over gx would be, since gx is 1 over x cube, then this value would be x to the power 5 plus x cube over x to the power 5 plus 4x to the power 4 plus 10. Then the value of this limit would be, as limit x tends to infinity, this value would be 1. Since this value is finite value, so obviously since 1 to infinity 1 over x cube dx is converges, we all of us know. Few minutes ago I have discussed 1 to infinity 1 over x to the power p is dx is converges when p greater than 1. Since here p equal to 3, which is greater than 1, so this improper integral is converges. And since this improper integral is converges, so our given integral is convergent. Here I have considered gx equal to 1 over x cube because notice in numerator the highest power of x is 2 and in denominator the highest power of x is 5. If we consider gx equal to 1 over x cube, then in numerator and in denominator the value of highest power of x would be same. Then we can evaluate the limiting value. Limit x tends to infinity fx over gx, we can evaluate this limit easily. Okay. I hope my all viewers have understood limit comparison test easily. Now consider this improper integral. Here fx equal to this. Now how we will choose gx? Notice in the highest power of the denominator is, at first we can write this as x to the power 1/3 times x to the power 1/4, then this would be 1 plus 1 over x to the power 1/4. Then highest power in the denominator is x to the power 7 over 12. Okay, and then limit x tends to infinity, since here the discontinuity has at the point infinity, so here limit x tends to infinity fx over gx, this value would be, limit x tends to infinity, this value would be 1. And since the limiting value is finite, so by limit comparison test, since gx equal to 1 upon x to the power 7 over 12 and this value is obviously less than 1, 7 upon 12 is less than 1, so we all of us know integration 1 to infinity x to the power p is convergence when p greater than 1 and when p less than 1, this integral is diverges. Since here p less than 1, so by p test we can tell this improper integral is divergent. So since this integral is divergent, that means our given integral be divergent. Then our next example is that fx equal to integration 0 to 1 e to the power minus x over x to the power 1 minus a dx. At first notice here 0 is point of infinite discontinuity when the value of a less than 1. That means when the value of a less than 1, then 0 is the infinite discontinuity. Now consider fx equal to e to the power minus x over x to the power 1 minus alpha. Now how we can choose gx? Consider gx equal to 1 upon x to the power 1 minus a. And since here the infinite discontinuity at the point 0, so here limit x tends to 0 plus fx over gx, which is equal to limit x tends to 0 plus e to the power minus x upon x to the power 1 minus a over x to the power 1 minus a, which after putting the limit, this value would be 1, which is not equal to 0. Therefore, since this value is not equal to 0, therefore since integration 0 to 1 upon x to the power 1 minus a and integration 0 to 1 upon x to the power 1 minus a, since here discontinuity at the point 0, so this integral would be limit b tends to 0 plus integration b to 1 dx upon x to the power 1 minus a. And obviously this type of integral is look like 1 upon x to the power p, here the integration 0 to 1. And we all of us know when integration 0 to 1 upon x to the power p, this is convergent when p less than 1. Since here p equal to 1 minus a, therefore this is convergent 1 minus a less than 1, that imply a greater than 0. Hence by comparison test of limit type, we can tell this fx is convergent when a greater than 0. I hope my all viewers have understood this type of question easily. Okay? Oh well. Now I will see one question which had come in CSR net. The question is, for p belongs to real number, consider the improper integral ip equal to integration 0 to 1 t to the power p sin t. Then which of the following statement are true? Option 1, ip is convergent for p equal to minus half. Option 2, ip is convergent for p equal to minus 3 over 2. Option 3, ip is convergent for p equal to 4 over 3. Option 4, ip is convergent for p equal to minus 4 over 3. Here ip equal to integration 0 to 1 t to the power p sin t dt. First, consider p equal to minus half. Then ip equal to integration 0 to 1 t to the power minus half sin t dt, which is equal to integration 0 to 1 sin t over square root of t dt. Okay? And we all of us know 0 less than equal to sin t less than equal to 1, and this is equal to integration 0 to 1 dt over square root of t. Since here p equal to half, we all of us know, few minutes ago I have seen integration 0 to 1 t to the dt over t to the power p convergent when p less than 1. Since half less than 1, so this integral always convergent. And by comparison test, this is less than equal to integration 0 to 1 over square root of t dt, and I have seen this integral is convergent. So by comparison test, we can tell this integral is also convergent. Okay? Now consider p equal to minus 3 over 2. Then ip equal to integration 0 to 1 t to the power minus 3 over 2 times sin t dt, which is equal to integration 0 to 1 sin t over t to the power 3 over 2 dt. And we can write this as t times t to the power half sin t. Notice in this integral has the discontinuity at the point 0. Also in the integral 0 to 1 sin t upon t, we all of us know this is the proper integral and this value is 1. So consider gt equal to integration 0 to 1 dt over t to the power half, and this is considered ft. Then since this has infinite discontinuity at the point t, so limit t goes to 0, ft over gt, this is equal to limit t goes to 0 sin t over t to the power 3 over t times 1 over t to the power half means t to the power half, and this is equal to limit t goes to 0 sin t over t, here t to the power half over t to the power half, this value would be cancelled and this value is 1, so So this is the finite value, and since integration 0 to 1 dt over t over half, here this is obviously convergent. This integral is convergent. So by limit comparison test, we can tell our given integral is also convergent. Okay. And consider p equal to 4 over 3. Then ip equal to integration 0 to 1 t to the power 4 over 3 times sin t dt. Obviously this integral is proper integral. So always there exists finite value, and this type of proper integral, since there exists finite value, obviously convergent. And fourth option, p equal to minus 4 over 3. Then ip equal to integration 0 to 1 sin t dt over t to the power 4 over 3. This is actually similar to second option. Here this is ft and t to the power 4 over 3. We can write this as t times t to the power 1 over 3. Since sin t over t equal to integration 0 to 1 is always 1, this value. So consider gt equal to 1 over t to the power 1/3. Okay. Since integration 0 to 1 over t to the power 1/3 dt, this value is always convergent, because here p equal to 1/3 and which is less than 1. So this integral always convergent. So right option. That means option 1, option 2, option 3, option 4, all are right option. I hope my all viewers have understood this question. This is very interesting question and very easy type question. Okay. Today I will stop here. In my next video, I will discuss other method of improper integral.